Hi, I'm Neil Greenspan. I'm a professor of pathology at Case Western Reserve University and senior editor at Pathogens and Immunity. And I'm here today with Erica Ollmann Saphire, president and chief executive officer of the La Jolla Institute for Immunology, to talk about her work on hemorrhagic fever viruses and SARS-CoV-2. And she'll be speaking about these topics at the Keystone Symposium, Lessons from the Pandemic, Responding to Emerging Zoonotic Viral Diseases.
We don't know what virus is going to cause the next pandemic. It might be this family or that family. It might be a reemergence of something we already knew. It might be something entirely novel. But we do know the human immune system is what's going to have to respond. And so the body of knowledge that we have built as a field over the last few decades of how do B cells respond, how do T cells respond, what are the differences between neutralizing and non-neutralizing activities in the antibodies, how do you develop a vaccine that will actually give you a longer lasting memory response, the arms of the immune response that you need to put together and coordination of those. All of that will be applicable to the next pandemic too.
How did your work on Lassa virus and other hemorrhagic fever viruses prepare you for the switch to research on SARS-CoV-2 and the current pandemic?
The body of knowledge built by studying HIV and flu and respiratory syncytial virus and Ebola and so many different pathogens, and figuring out how do you stabilize these kinds of molecules? How do you evaluate the kinds of glycans around the surface? Do the most potent antibodies block receptor binding, block cleavage, block conformational change, do something else? How do we assess which parts of these molecules don't change much through mutation? Do some of the more potent antibodies bridge epitopes? How do we develop tools, for example, in structural biology, that let us appreciate the conformational complexity of these things? And what protein engineering strategies do we use to make better immunogens? A lot of the fundamental ideas about how do we figure out how to capture, stabilize, and image the HIV surface envelope could be used and repurposed in trying to understand how do you make an RSV vaccine? How do you stabilize SARS-CoV-2 to make an immunogen that's going to work, or a reagent for structural biology?
But if we had a new pathogen where we did not know if there was more, especially if there was more than one surface glycoprotein, where we did not know which was the target, do you think it's fair to say it would have taken, or it would take much longer than was the case for SARS-CoV-2 to get a vaccine? I mean, even with mRNA technologies.
We wouldn't have mRNA vaccines this year if people hadn't been tinkering with them for 20 years to figure out how to formulate them, how to package them, how to cope with innate immune responses. So things very much build on the shoulders of prior efforts. And for a lot of pathogens, we don't really know what the right vaccine formulation is going to be. mRNA may work for some things and not others. A VSV vectored vaccine may work for some things and not others. And so one thing that was pretty successful, I think, in advancing vaccines so quickly against SARS-CoV-2 was the fact that in parallel, different groups could make and evaluate different things. mRNA, protein nanoparticles, adenovirus, other kinds of vectors, and activated virus. And if you don't know what's going to work, running lots of horses in the race at the same time is a good way to make sure that some are going to get over that finish line.